Thank you. It's a great privilege to give a talk. I'm going to try to go in a different direction than sort of, I guess, the more applied and detailed talks in the past few days. Kind of go back to the roots of Shannon theory and just general error correction theory before zooming into this class of codes that we're working on. So this is the second of three, I guess, bosonic talks. So put on your bosonic hats. So let's maybe go back and remind ourselves what classical and quantum codes are made of. Classical code words are basically some subset of some set of elements that people there like to call an alphabet. And here are some examples that many of which you probably are very familiar with in classical coding theory. They don't always have to be bit strings. They can be fields or rings. And if you go back to the original, motivation for Shannon theory, was communicating across analog channels, so basically using real numbers. Now, something that's not, I think, is appreciated enough, so I wanted to flash it here, is that you can think of quantum code words as being defined by functions on the same alphabet. In this context, the alphabet's called the configuration space, but you can just call it as functions of the alphabet. So classical code words are elements, and quantum code words are functions. And here's the corresponding state spaces on which you have a Pauli-like structure that you all are familiar, well, some of which, again, you all are familiar with, that are used in various corners of different communities. So I thought it might be useful to connect these and just list them over here. And there's a big difference between fields and rings. We can talk about that offline in both columns, actually. So once you have this alphabet, how do you pick the subset? Well, oftentimes your errors just map you to different elements in the alphabet that are like close enough or far away in some metric. And the metric's usually like some Hamming-like, or Euclidean-like distance metric. So if you think about that type of metric, then you're basically reducing coding theory or picking the error correcting code to a packing problem. You want to have some amount of code words, and you want to distribute them some even way with respect to the metric, such that when you have some error, you can still distinguish where the code word came from, and so recover the information. So this lends itself to a geometric perspective, at least for low dimensions. So for example, here I've drawn the 8 different bit states of the repetition code in this thing called a Hamming cube. So the dimension of the cube will be the number of bits. And the two states of the repetition code here are just these opposite corners. And you can see that they're far away from each other in this metric that's implied by this cube. And this blue region, just as a side note, is called the Voronoi cell. It's the set of all elements that are closer to the all 0 state than the all 1 bit string. And that basically kind of tells you how much wiggle room you have under noise that shifts you around, under bit flips in this code before you get to the Voronoi cell of the other logical bit. And then you can't recover correctly. So you can maybe do one more before this gets pretty wild. So here's a 4-bit single parity check code. And you notice maybe if you stare at it a bit that there's also some spacing and some Voronoi cell stuff going on there. If you upgrade to real numbers, well, what are codes on real numbers that are analog to binary codes? Well, it turns out they're just lattices. They don't have to be evenly spaced, but for simplicity, here's an actual even-spaced configuration, which is otherwise known just as a lattice. And here, the context here, this is called the unit cell instead of the Voronoi cell, the blue region, right? And very early on, they had the problem of transferring information through analog signals of fixed energy wound up basically being equivalent to sort of cutting an ice cream scoop of the real Rn configuration space, looking at only like the boundary of it for fixed energy, and looking at the entire scoop for bounded energy codes. And that quickly grew into this field of spherical codes, where you're basically trying to pack things on a sphere in a way that's well separated, but and uniform, so that you can correct against noise. So I mentioned, so if we graduate to quantum, there's a very simple construction that's very general that you can take these codes already that we know and construct quantum codes. You just split the set of the code words and superpose them. Now, how you split them depends on what the alphabet, but I don't want to go into details there. But splitting and superposing them will give you code words of a quantum code. Now, the reason is the following. So to protect from bit flip, we already have the spacing in the classical code. So the corresponding quantum code will also keep that bit flip protection. But now, because you're storing superpositions, you also have phase flips to worry about, and the superposition will make sure that you have ways to map to error spaces under phase flips, and so you can detect and correct those errors. Okay, and this is, again, super general property that's valid for all four of these things. This is also, by the way, why you need entanglement for quantum error correction, because you have to superpose. So for, well, this one you don't get any, because there's nothing to superpose. You have two things, you split them, and you get just one ball per code word, right? But this one you can already probably see that you can split this one and you get the 422, the 4-qubit code. So you split these into four clusters of balls, one color per ball, and superpose those elements, and you get the 4-qubit code. With lattices, you get GKP codes. More generally, I think the appropriate name is quantum lattice codes. And what this work is about is filling in the square. Okay, this is what we do. We notice that we develop a framework that basically consists of constructing codes that are superpositions of points on a sphere, namely in a quantum system with a spherical configuration space. A quantum system where there's some sort of sphere in there. Okay, and we call them quantum spherical codes. I'll focus on uniform superpositions for this talk, and there's been some follow-up work by others that I'll mention where they do non-uniform superpositions. Okay, so this type of framework is applicable to any spherical configuration space, as I said. This includes things like coherent states. I'll introduce those if you don't know them, and all sorts of other coherent states, and molecules. Those are the ones that I found. There's going to be two types of noise, bit and phase flips, okay? And the bit flips are basically induced by rotations on the sphere. It's the usual kind of Euclidean classical situation, and you can quantify how well you protect against rotations by how well separated the code words are. So you can take distances and Euclidean distances between points making up code words, and you look at the minimum one, and that tells you kind of how well you protect against rotations. Phase errors, on the other hand, in general, can correspond to the environment trying to sense which code word you're in by applying a potential function to the sphere and seeing if the potential function can sniff out which code word you're in, right? If you're just only one code word is the north, one code word is the south pole, then a potential function like it's very easy to sniff out which one it is. You could just have a function that's 1 on this one and not -1 on that one. And more generally, you can organize these potential functions by some sort of spherical harmonics or whatever you want, what's more convenient for your sphere. So in this talk, I'll focus on the primary application of this, which I think is coherent state codes on a sphere, and otherwise these are just generalizations of the CAT code. So that's what we'll focus on today, but I just want to note that this is hopefully a very general framework. And this is well-motivated question. This is something I was thinking about, we've been thinking about since grad school for me. There's not very many few mode codes that have been developed, and it might be useful to do that both from the theory perspective, linking back to the classical code, to all this theory, and also from the experimental perspective, because there's this well-developed infrastructure in superconducting circuits and other platforms, trapped ions, et cetera, that has a lot of tools now that can be used to engineer these codes. So this is a review slide for, I hope, most of you, but this will cover the bare minimum to sort of understand what a coherent state is. It's just a Gaussian packet in the phase space of the oscillator, the position momentum space. Okay, you can't have a delta function because Heisenberg uncertainty, so you have to have these Gaussian things. And these you can make in the lab. It's very easy. And you can have them for any complex alpha. So alpha is usually the symbol you denote these with. The things I want you to know is that the overlap between them depends on the Euclidean distance between alpha and beta. Okay, so this is where the notion of distance in spherical codes comes in. It directly is now relevant to because it's also relevant to the overlap between the states. And in one mode, alpha is just a number. In n mode, which is what we're going to do, it's a vector, complex vector. Now, your notion of Pauli's is unfortunately out the window. So deal with it. But what's very beautiful is these lowering and raising operators. The coherent states actually are left eigenstates of them. And so when you apply a lowering operator to a coherent state to kick out a photon, you get the state back with alpha in front of it. And there should be alpha sub j applied to a vector on the left there. As far as x-type operators go, at least now they are unitary. Again, they're not like some Pauli's, but they're in the case we're going to be studying here, they're rotations. So while you probably recall from last talk, the relevant operators were translations because we're dealing with lattices. Spherical codes are stabilized by subgroups of rotations. And these correspond to what's called passive linear optical transformations. The jargon is beam splitters, phase shifters, whatever. They look like that for a single mode, and then there's just some, I'll just abstract away the details. They're exponentials of quadratic operators, and they directly rotate the vector of alphas inside the configuration space, denoted by the alphas. And spherical code for us is just some subset of points on a sphere. So the spherical constraint here is just that the norm of alpha is fixed to some constant. We'll fix it to be 1 for reference, okay? And then, so we'll handle everything with a unit sphere, and then we can just blow up the sphere whenever we want, which is equivalent to pumping energy into the sphere in the experiment. So the first class of codes is it will be based on polytopes, which are subsets, which are well distributed points that whose vertices form polytopes on the sphere. And the original cat codes are basically two-dimensional real polytopes, and we'll handle some cases. So now we can throw in these new cases where we go into the multi-dimensional situation. And just remember, these are just vectors, so there's nothing really crazy, just hard to visualize them past 3 dimensions. So let's review the simplest cat code. The simplest cat code is in 1 mode, so it's 2 dimensions, and the simplest way to is basically the kind of a repetition code in 2 dimensions. You just place 2 points antipodal to each other at alpha and minus alpha. And this is something that has been thoroughly studied theoretically and experimentally for a while. I'll just mention some highlights. Regarding stabilization, remember we don't have these nice Pauli's, so there's not really a very simple way to measure and correct in discrete fashion that you all are familiar with. However, there's this beautiful equation from quantum optics dating like 30, 40 years ago, which is a Lindblad, which basically imposes a double well potential on your plane, on your phase space, whose wells are the 2 states in the minimum. And it's been realized experimentally, and this is actually something that offers some protection from small rotations of the states, because the wells, this thing will actively stabilize the things in the wells, and if you have some perturbation taking you out, they'll leak back in without inducing any error. So, and if you see, you can see the reason this stabilizes these 2 states is because this jump annihilates the 2 coherent states, and it doesn't care about the sign. And the logical gate will just be the square root of that. Now remember, we have some unitaries to go for the X-type stabilizers. These you can try to apply and measure in some discrete fashion, and so here you have a rotation that just exchanges the 2. Okay, so now let's go to, again, something that's known. Now you have more than 1 code element of the constellation per code word. Here you have 2. And these make 2 antipodal points that are superposed respectively. Together they make what's known as the vertices of a square. And the resolution, or so you can quantify the minimum, the protection against rotations by the minimum distance between vertices in the respective constellations. Since you have more than one point in the constellation, you can protect against some loss and gain errors, which are potential functions on the sphere. And you can see maybe roughly that there's now going to be a trade-off. The more points you include, the closer they will be, the smaller the protection against rotations. But the more points there will be, the higher degree monomial you can protect against with respect to loss. And there's also gates on these that are very similar, just higher power of A. And now you can do a little bit more rotations. You have a logical and you have a stabilizer, the parity, which has been measured in experiment and tracks the states. Okay, so in terms of the new codes, here's the simplest extension to multiple modes. You have a 2-mode constellation, and each code word corresponds to the 5 vertices of a simplex. If you look at the resolution, the point here is to use multiple dimensions to get higher resolution at less energy. In this case, the simplex is not so good. It's lower than that of the 4-component cat, but it detects slightly more losses than the 4-component cat, but otherwise it's kind of not very well performing. I just want to flash the stabilizers. Now you start to have two-mode monomials, and you start to have 2-mode rotations for the logicals and the X-type stabilizers. With simplices, there's an infinite family of them, so we can extrapolate this and have an infinite family of codes that will approach the resolution of the 4-cat while having the extra detection power. So to get really outperforming codes, we have to go to maybe more exotic polytopes, such as the Hessian. This is a 3-mode code. Its resolution is the same as a 6-component cat. However, it detects more and corrects more losses than the 6-component cat. So presumably at the same level of same energy of the sphere, you should be able to do more against the dual source of noise. It's got beautiful stabilizers and z-logicals related to some stuff from I think, algebraic geometry that I don't want you to ask me about. And what I wanted to point out briefly here is that this is the first code we see, at least I've seen in bosonic, that the degree of the stabilizers is less than that of the logicals, at least in some of the cases here. So you know the surface code, the degree of the weight of the stabilizers is 4, but it can correct much more than weight 4 errors. And this is something you don't see in the cat code, but this is something you do see here. So presumably there's some sort of extra quantumness or some feature here that might be interesting to exploit. And it's got 3-mode stabilizers and stuff. So besides coherent states, there are other types of states that one can try to use to construct codes, and also ensembles of states that one can try to measure. One of these has also been the phase state. This is responsible for the number phase codes by Grimsmo, Bergiola, and Combs. And one of the things that we did here in parallel was generalize these phase states, which you can think of as rays in the 2-dimensional phase space, to now rays in the n-dimensional or 2 n-dimensional phase space of n oscillators. I call them the spherical states. And they're useful, the ensembles of these states are useful for logical Z measurements. So spherical codes are a bit trickier than lattice codes, admittedly, because they use quadratic generators as opposed to linear. And there's kind of a very drastic differences in the number of stabilizers and logical gates that they can do. So the good news is that there's lots of interesting logical gates these codes can do. I'll shine two different codes that have 2 different logical gates, sets, the L there. One has 60 and one has, stabilizers. The logical is one has 60 and the other has 2. The bad news is that the ones that have a lot of logical gates, they don't have a lot of stabilizers. So a given rotation will either do or do not something, and there can be extreme cases of when we simply don't know how to measure syndromes for the code because there's just not enough stabilizers. And that depends all on some geometry of the polytope used to form the code word. Now, you can also use the USCs to reinterpret pre-existing codes. What was done in concatenated cat codes with CSS codes in that literature was that people calculated some properties of the individual physical qubits of the inner continuous variable code and then quickly graduated to the outer code, which was made of qubits, so that they can handle it using normal qubit-based language. However, the QECs allowed us to sort of see the advantages of backing up and looking back at the full code and realizing that it's actually a point in R2N. So one of the features this offers is, besides connecting to things from classical coding theory, is this one, this CSS type stabilizer of Lindblad form. Just like the double well we saw, but now it's utilizing the parity checks, the Z-type parity checks of any CSS code. So it's geometrically local, or whatever, however local as the underlying CSS code, and it's not too difficult to engineer. It's doing the same type of engineering as people have thought about at Yale and Amazon and other companies for a while. And this is not something that I think people have appreciated before. So with that, we studied a bit of the polytope CAD codes. The concatenated CAD codes connect to CSS codes and offer some new ways to do their gadgets, at least the Z-type. Not the X-type still have to be measured in the usual way. The Z-type can be done continuously. And there's some connections potentially to, all your favorite CSS codes there. And then there's this general framework. I want to acknowledge here, this was motivated by reading classical coding theory, but also by Anthony Leverrier et al. Paper on the 2TQ trit, which was the first two-mode CAD code that I'm familiar with, that used group-type constellations. And there's a follow-up by Anthony, actually, about the gates where they use non-uniform superpositions of a QAC to show that you can have lots of different types of gates, including Clifford group and others. This hopefully will be extended to, or hopefully we can extend it to more general spaces to sort of generalize the geometric picture I showed you in the beginning. So with that, I'll thank you for your attention.
Any question?
Pavel over there.
Thanks for a very great talk. So my question is about, do you have currently some maybe general bounds on the parameters of your spherical codes?
Right. We're working on it.
Something like Gilbert-Barsham bound or some upper bounds?
Yeah, so my student's working on it. If he was here, I would make him answer, but at the moment, no. But there's some stuff we're working on. I agree there's lots of spherical code bounds that we'd love to adapt to quantum, so I'm happy to talk about that.
Okay, thank you.
Spherical designs. Sufficient condition for good protection against loss and errors is being a spherical design. So if you just take spherical designs and make them into constellations, superpose them, you automatically have a reasonable code.
I'm wondering if you have any intuition on the gain of this approach compared to the previous concatenation with qubit codes in terms of performance.
Yeah, it's a bit apples and oranges. So so we're comparing polytope and CS. Are you talking about the CSS versus polytope or the?
I'm talking about concatenating GKP.
Oh, GKP. That's even more apples and oranges. I'm not sure. No, we haven't compared. We've only compared to the current CAD codes. I would say GKP codes, philosophically, they use more of the phase space. They use the internal part of the sphere as well, right? They pack it with a lattice, right? While spherical codes only look at the surface. So the surface area, is quite big in the limit of a large number of modes, but still, they're not using the internal part. So I feel like GKP codes would still be outperforming. Also in the classical coding theory, GKP or lattice codes, I think have higher achievable rates than spherical codes. So that would be my naive guess.
Maybe even more generally, I have a bunch of oscillators. How using encoding into multiple oscillators simultaneously improves the performance? There is a gain, right? You expect a gain.
Right, so the question is, I guess, what is the gain for using multiple oscillators? So in this talk, I phrase it in terms of the coding parameters. So you have more surface area in multiple modes, and so you should be able to, sort of spread out your states in a way that doesn't use up much more energy than you had in the cat code case, because there you don't have a lot of room. Okay. Now, so that's what the parameters were suggesting, right? But now, if we look at numerics, it's interesting. So basically, polytope QSCs, we have some preliminary numerics. Polytope QSCs allow you to have higher performances in regimes where cat codes would not have performed as well, but at the price of slightly more energy per mode. Okay, so you do actually have, we are seeing you gain in terms of now the whole code class performs better, but you also have to, with more modes, you still have to blow up the sphere a little bit more to resolve. So I don't understand that. Okay. So we're still working on that as well. Yeah.
Hey, Victor.
Hey, Shraddha. How's it going?
Great dog. I love multi-mode codes. So great. Some great.
Is that a comment or just?
No. I have a question. So I think it's analogous to Pavel's question and Nicola's question right now. Did you find that these spherical codes are more compact in the sense the ratio of physical codes logical qubits and physical qubits is upper bounded by a smaller number compared to the discrete variable codes? This is in relation to the Gilbert-Verschamuth bound and the Hamming bound that you generally see for discrete variable codes.
I'll just flash this table in response to that. We've seen, like, what we've done is mined all the polytope literature and some classical codes, and we've just found the code parameters, and what I can say is that we see all sorts of shapes and sizes here. Okay, so I don't know if I have some, again, I don't have some universal bound, but you can look at things at the bottom, like this Hadamard code-based polytopes, where you see things expanding, blowing up with some parameter r exponentially, and then look at things like the demicube and the simplex, where things are linear. And we don't have like a code for any family of parameters, but there's definitely some room to sort of explore there and try different other constellations. Okay. I can't answer your question, really, sorry.
My question was basically coming from the comment in the GKP paper itself. So when they talk about encoding logical qubits in the multiple qubit levels, so this is not multimode qubit. I have a qubit, and I'm encoding a qubit in those qubit levels. It's given that you just need 18 levels to correct all types of errors, which is lesser than the requirement of the 5 qubit code, which is the smallest error correcting code you can have for discrete variables. So that sort of shows how compact CV error correction could be. But I don't have an analogous result for multi-mode codes, and hence the question.
Yeah, those are discrete, so it's easy to just count things. These are continuous and can be blown up, so it's hard you have to look at surface areas of spheres and volumes and things. And yeah, that's a good question. I would agree we need to figure that out.
Great, thanks.